All right, welcome. So we're starting now with power series, which is very similar to Taylor series. They're the same in a lot of cases, but slightly different. But a power series is just any expression. Let's write this as y. Power series is any expression y equals sum n goes from 0 to infinity, a sub n, x minus x0 raised to the n. Okay, so now there are actually three different things as far as convergence goes. Okay, first case, the sum okay, this converges for some real number, for actually x minus x0 less than some L, okay? And we actually could take L being anything from 0 to infinity. And we actually even include infinity, okay? So let's take a look. This is actually three different cases that you saw in Calc 2, okay? So first case, L equals 0. That means that our sum is actually going to end up just being equal to a sub 0, okay? Why? Because every other term is going to be 0, okay? When n is 0, this is 1. However, for every other case, then this is going to be 0. So this means that this is where the series converges just at x equals x0. Okay. The second case is that you could have some non-negative and non-finite L. So you could have some L between 0 and infinity, okay? And so this series okay, converges on the interval x minus L to x naught plus L. When I write this like this means x is in the interval. So this is equivalent to saying, for example, x naught minus L less than x less than x naught plus L. Okay, those are equivalent statements. Okay. Third, you could have L equaling infinity. Okay, you could have L equaling infinity, and that means that the series converges everywhere. Okay, so from negative infinity to infinity. Okay, and this L is called the radius of convergence. Okay, this may be ringing some bells from Calculus 2. I know that was a while ago. Okay, Now, you can actually find the radius of convergence given the series. Okay, so if you have our series, let's write it down. Okay, so it has radius of convergence. And the radius of convergence is given by the limit as n goes to infinity, the absolute value of a sub n over a sub n plus 1. Oops. Okay, let's sort of see, this isn't going to be a proof, but it's going to be sort of an idea of what's going on, okay, or why that happens. Let me make a little more space. Okay, so what's going on is if we have this series, okay, and if we assume, this isn't a proof, I would say this is more like a heuristic argument. Okay, so if we have this and this happens, okay, then what's going to happen is this is going to equal, let's take sum, n goes from 0, let's cut it off at some n, a sub n, x minus x0 to the n, plus the sum, n goes from n plus 1 to infinity, a sub n, x minus x0 to the n. Now, if this is true, if the limit as n goes to infinity of a sub n over a sub n plus 1 equals L, then basically what I'm saying is at some point, it's like you're just taking L to the n, okay? Eventually, okay, we are taking a sub n, okay, equals L to the n, okay? Think about it this way. If you have a sub n divided by a sub n plus 1, oh, I think it's 1 over L sub n, sorry. Okay, if you say this is basically L, okay, that means a sub n plus 1 is basically a sub n divided by L, right? Okay, and now if we take a sub n to be L to the n and a sub n plus 1 to be L to the n plus 1, that fits. Okay, watch what happens. So if I take that, this is basically 1 over L to the n plus 1 is basically 1 over L to the n times 1 over L. And that's true, right? So we're basically saying that this is the basic idea. Okay, it's not exactly that, but it's close enough for, you know, the sort of work we want to do. Now, then, this part is finite, so we really don't care about it. This is some, let's call it k. Plus, we're going to take the sum, n goes from n plus 1 to infinity. A sub n, we're going to say that's basically 1 over L to the n. X minus x0 to the n. So now, if x minus x0 is small enough, this basically is like a geometric series. Okay. All right. We'll start doing some problems in the next video.